Here we go. I think my, what do you call it? Thing's knocked out. I got this thing in the way of it. There we go. Actually, I don't want it up there. I want it down here. Yes. So what we're going to do today is work on more advanced probabilities. And we're going to look at probability rules and probability trees. And these are kind of the list of things I want to get covered, or at least try and get covered for today. So we're going to do the definition of what's called mutually exclusive events and independent events. So we're typically going to be looking at two events rather than just one, two or more events rather than just one. So let's do mutually exclusive. Something's wrong with this thing. It's driving me crazy. There. So here's the definition. Two events, A and B, are called mutually exclusive events. We normally just call them AME for short. If they do not share any common event, events, events, I guess I'll have to call it. Let's give you an example. Suppose A was a probability, or let's say A was the event that you picked a card and the card was a king. And let's B be the event that the card was an ace. A and B are mutually exclusive. Would you agree that if you're a king, you can't be an ace, and if you're an ace, you can't be a king, right? Now, there are four kings and four aces, right? But they're mutually exclusive, right? If you were drawing a little picture, couldn't that be all the aces and that would be all the kings, right? They're separate, right? You can't be one and the other at the same time. That's what mutually exclusive means. Now, there's a test for it. The probability A or B is the same as the probability of A plus the probability of B. So for instance, if I wanted to find out what's the probability that I get a king or an ace when I pick one card. Okay, we know there's 52 cards in a deck, agreed? Now, the word or in statistics means one or the other or both. So there are four kings in a deck, there are four aces in a deck, and that comes out to be 8 out of 52. Now, if I find the probability of a king, and I add the probability of an ace, a king is 4/52, an ace is 4 out of 57, and that is also 8 out of 52. Now, the fact that these are the same proves to me that kings and aces are mutually exclusive. I think it's pretty obvious that kings and aces are mutually exclusive, but can you imagine situations where we tell you this? If I tell you that the probability of event A or B is 0.9, and I tell you that the probability of A is 0.4, and the probability of B is 0.5, right? So if I tell you all of those things, the conclusion that we can come to is that A and B are mutually exclusive. And isn't it simply because these two add up to that guy? Right. So two events are mutually exclusive if they don't share any common events. And you can test for it by finding the probability of A or B. And if it's the same as just the two individual probabilities added together, you are mutually exclusive. So let's show you something that's not. Suppose A is that you pick a card, and the card was a king. And B, you pick a card, and the card was red. They are not mutually exclusive. Aren't there some kings that are red? Aren't there some red cards that are kings? You can phrase it either way you want. They're definitely not mutually exclusive. So if I went and said to you, what's the probability of you getting a king or a red? So let's put that in English as well. What's the probability that you pick one card and it's a king or it's a red card? This is not the correct calculation. Oh, there are 4 kings and there are 26 red. So the answer should be 30 out of 52. That is not correct. I call this double dipping. Aren't you counting kings and reds twice? Aren't you some cards are counting twice? How many red kings are there? 2. So shouldn't the correct answer be 28 out of 52? Now, if you calculate the probability that you get a king or a red card and you do it correctly, the answer is 28 out of 52. If you find the probability of a king on its own, there are 4 of them out of 52. And if you find the probability of getting a red card on its own, there are 26 out of 52. And if you add these together, do you see that the answer you get is not that one? Isn't that your test that we talked about for things to be mutually exclusive? And the test is this thing here. If the probability of A or B is the same as just adding the 2 together, they're mutually exclusive. If you find them separate and add and it's not the same as it is here, they are not mutually exclusive. And so that's important if you want to calculate probabilities, to know whether your events are connected in some way, right? They're not mutually exclusive, because the way you count, you have to be careful, right? Don't double dip. Don't count red kings twice, you know, that kind of situation. Now, the next one are called independent events. So, 2 events. Say A and B are independent if the outcome of A has no effect on the outcome of the other one. When we're talking about the outcome, we're talking about the probability of it happening. Now, there are different kinds of situations where independent crop up. Suppose A is the event that it's going to rain on Tuesday. And let B be the event that I win the lottery. Would you agree that if it rains tomorrow, the chances that I win the lottery are exactly unchanged as if it didn't rain tomorrow? Would you agree raining has no effect on me winning or losing the lottery? Would you also agree the other way around it's true, right? Me winning the lottery today won't make it rain tomorrow any more or less than it was going to rain tomorrow anyway, right? Those are examples of two events which are not only independent, which agree that they don't even have any connection, right? They are mutually exclusive. But you can also get events that use what's called a conditional probability. And this is how you write a conditional probability. A thingy B, A given B. So you read that out as the probability of A happening given, that's what that vertical line means, given that you already know that B has happened. And we call these conditional probabilities. So I'll give an example of a conditional probability. What's the probability that you get a king given that it was a face card? So suppose I tell you, I know the card is a face card. What's the probability it's a king? Now, if you don't know a lot about cards, which is possible, a face card is a jack, a queen, or a king. And I think they're called face cards because they have pictures of people's faces, right? A jack's a guy and a queen's a female and so on. Now, there are actually 3 in each of the 4 suits. So this is how you calculate this. If I tell you it's a face card, that means there's only 12 cards, right? There can only be 12 cards that could have been harmed, right? If I tell you it's a face card, right? Now, what's the probability it's a king? Well, out of all those 12 cards, would you agree that 4 of them are a king? So the conditional probability that you get a king, given that you know that it's definitely a face card, is 4 out of 12, which would simplify the third. Now, if I went and said to you, what's the probability that it's a king given that it's a red card? Well, can I just say there's 26 red cards, 13 diamonds, 13 hearts? How many kings are there out of those 26? 2, right? There's a king of diamonds and a king of hearts. And that simplifies down to 1/13. Now, I'm now going to just find the probability of getting a king, right? A normal, boring, single probability. This thing needs to be up higher. That's what the problem is. There. Okay. What's the probability then that I get a king? Just a normal king. 52 cards, 4 are kings. And, oh, have you noticed that those 2 are the same probability? So the probability of getting a king is 1 out of 13. The probability of getting a king, given that it's a red card, is also 1 out of 13. So we would say that these 2 events are independent. Getting a king and getting a red card don't affect each other. If I know it's a red card, the chance that I get a king is still 1/13. Has no effect. So we have a test that we use for independence, and it basically says, if the probability of A given B is the same number as the probability of A, then we can conclude that A and B are independent. So probability independence might not be the same thing that you think is independent, because a lot of people think, well, both of them are cards, right? And one of them's kings and the other one's reds, and there's some red kings there, right? Surely they are connected in some way. How can they be independent of each other? Independence, probability independence, just says that this thing doesn't get affected by the B. Would you agree the answer is the same whether you knew B had happened or not? So the events don't need to be mutually exclusive. So now I'm going to show you a bit of theory, which kind of freaks people out, but it's actually very simple. Suppose I take A, and what shall I pick for A? Well, let's pick A and B are mutually exclusive events, okay? So if you're A, you can't be B. If you're B, you can't be A. If I asked you to find the probability of A given B, the answer is going to always be 0. Would that make sense? Suppose A was red cards and B was black. What's the probability you get a red card given that it was a black one? Ain't going to happen, right? If you're mutually exclusive, this is 0. Now, suppose A and B are independent. Then won't the probability of A given B be the same as the probability of A? So 2 events that are independent, this is true. 2 events that are mutually exclusive, this is true. Do you see that you get a different answer to the conditional probability? So here's a little puzzle. If A and B are mutually exclusive, and I tell you that the probability of A is 0.3, then what will be the probability of A given B? What will the probability of A given B if they're mutually exclusive?
Zero.
It's always 0. Does that matter that it's 0.3? No, it's still 0. If it's 0.7, still 0. Now, if I tell you that A and B are independent, and I tell you that the probability of A is 0.3, you should be able to figure out what that probability is. Yeah. So are you separating in your brain the independent and mutual exclusive are different things, right? Different concepts, right? Mutually exclusive, the 2 events share nothing in common, right? If you're one, you can't be the other, right? Independent is the probability of A and B do not affect each other, right? Probability of A given B is still the probability of A, right? One does not interfere with the other. Right? And that would be an example of that. So let's show you what these types of things look like in homework questions, right? So you can say, oh, okay, that's how they ask me. So I hope you're looking at if 2 events are mutually exclusive, right? So if 2 events are mutually exclusive, can they occur concurrently? That's a weird word, but the answer is no. Okay, if 2 events A and B are independent, and you know that that guy is 0.55, then what is the value of A given B? That's very similar to the one I just told you a moment ago. Wouldn't the answer be that? Right, if you're independent and I tell you that the probability of A is 0.55, the probability of A given B is also going to still be 0.55. Now, here's a question. the probability of A is 0.4 and the probability of B is 0.3. If A and B are mutually exclusive, what would be this guy? Well, if you are mutually exclusive, isn't the probability of A or B just the two things added? In which case you'd get 0.7. Are we good with that? Any questions? If you're mutually exclusive, the probability of A or B is the probability of A plus the probability of B. So in this case, it would be 0.7. So now going to show you some more probability rules. And I think I probably should put them all together. Right. If you are mutually exclusive, so we have two events, A and B are mutually exclusive. The probability of A or B is the probability of A plus the probability of B. Right. So far, so good. I'm just changing some things here. Now, if you're almost equal, what is the probability of A given B? It's always the same answer. Big fat zero, correct? Right? In fact, isn't that the test that you typically use? Right? You could use this test as well. Now, if they're not mutually exclusive, right, so they share something in common, then how do you calculate the probability of A or B? Well, it's a probability of A plus the probability of B, and then you take away the double dips. And the double dips are A and B, which basically means the probability of both happening. Right. So when we did the card one, didn't we have kings or red kind of thing, right? And so that would be the kings, the red, take away the red kings. That's what that would look like. And okay, are we cool with that? Now, if you are independent, so if A and B are independent events, then the probability of A given B is just the probability of A, right? What do you think if I wrote it the other way around, which you don't typically do, but just out of curiosity, what do you think that would be equal to? If they're independent, what do you think the probability of B given A should be?
B.
Yeah. And this one, you might not figure out. But what do you think the probability of A and B happening? Well, you do that. You if they are independent, at least, you multiply them together. So when they're mutually exclusive, you typically deal with ors or conditionals. And when they're independent, you typically deal with ands or conditionals. So there is a homework question. I'm just going to write down. Suppose I tell you that A and B, right? And I tell you that A and B are mutually exclusive. And I tell you that the probability of A is 0.4 and the probability of B is 0.3, and I also tell you the probability of A and B is 0.1, then you can calculate the probability of A or B. Now, since the events are mutually exclusive, these are the rules that we would use to work with them. And can you see this rule here is how you find the probabilities of an OR, and I'm saying not mutually exclusive. So it's going to be A, it's going to be B, and then you're going to take away the A and B guy. So it's 0.4, 0.3, and you take away a 0.1, and so that would be 0.6. This is a version of question 4 then. Do something here. Don't know if you could hear background sound, but my wife was talking and I could hear her. Don't know if you could. Could you hear my wife? Yeah, she wasn't talking about anything interesting anyway, but she's talking to her sister, I think. She's always talking to her sister. She's got 3 of them, so. Suppose I tell you that this guy is 0.6, and I tell you that this guy is 0.8, and I want to know, well, first I'll have to tell you that they are independent. And now I want to know the probability of getting A and B. Now, because they are independent, can we use this rule? So it's going to be 0.6 times 0.8. So the probability of that event happening is 0.48. So if 2 events are independent and you want to know what's the probability of both of them happening, the answer is this times this. Put a story on that. That might help. Suppose the probability that it rains tomorrow is 0.2. And let's suppose the probability that I wear red tomorrow is 0.3. So what's the probability that it rains tomorrow and I wear red tomorrow? Right, would you agree first that rain, whether it rains or not, or whether I wear red tomorrow or not, would you agree that they are not connected, right? There's no reason I would change the colour and depending on the weather. So we can say that this is A and this is B, and we're going to do an AND. So it would just be simply multiplying the probability it rains by the probability that it's red. And that would be a 0.2 times a 0.3, which ends up being quite a small chance of happening. Isn't there only, what, a 6% chance that it rains and I'm wearing red tomorrow? Right? Multiplication goes with independence. Now, here's a new formula we're going to use. If I also tell you, right, let's use this one here. If I also tell you that the probability of A given B is 0.9, right? Let's see what information I can get you. I'm telling you that that's 0.6, I'm telling you that's 0.8, and I'm telling you that A given B is 0.9. Are A and B independent now? Now that's 0.6 and that's 0.8, but this is 0.9. Are A and B independent? Now, if they were independent, What would the probability of A given B be the same number as? Well, shouldn't it be 0.6? You see they don't match. So I can tell you these are not independent. See, that's question A, they were independent, right? But question B says, forget about A. Suppose instead I tell you this, what conclusion could you make? Suppose I told you this. What conclusion would you make this time?
Independent.
They are independent. You see, if this number is the same as A, they're independent. If this number is not the same as A, they are not independent. So I'm now going to show you yet another formula. Where's my little list? I should keep them all together. Yeah, here's my little list. Here's another formula that we can use. The probability of A and B happening is the probability of A given B times the probability of B. And this works, right? Whether the events are independent or not. This formula works in all situations. That the probability of A and B is the probability of A given B times the probability of B. So let me make a question using. Suppose I tell you the probability of A is 0.3. The probability of B is 0.5. And what else can I tell you? And I tell you that the probability of A given B is 0.2. Then I can calculate the probability of A and B. It's the probability of A given B times the probability of B. And so that's going to be A given B is 0.2 times the probability of B, which is 0.5. And so the answer here is 0.1. Are we good? Now, let's turn that question on its head just a little. Suppose I tell you the probability of A is 0.7 and the probability of B is 0.2, and I tell you the probability of getting A and B is 0.4. And I would like to find, using those three guys, the probability of A given B. Try to see if I've still got my list, Andrew. Where's my list? Oh, it's in front of me. So I am going to find a formula for finding the probability of, probability of A given B. And I can just actually rearrange this formula. Oh, it's a mess, I wish it wasn't. That the probability of A given B is this guy times this guy. So won't this guy be that guy divided by him? So if you want to find the probability of A given B, as long as you know what these two things are, you can calculate it. So in my case, A and B is 0.4, and probability of B. Can I switch these two guys around? There. And that answer ends up being whatever 4/7 says. So we have a list, that's this list here, that allows us to calculate quite complicated probabilities. Use these if you're mutually exclusive. This is true if you're not mutually exclusive. This is true if you're independent. This is true no matter what, whether it's mutually exclusive or independent, these formulas here work. So we have a list of choices depending on what the question asks us for. So let's see if I can find one. This is version of question 5. We are told the probability of A is 0.4. We are told that the probability of B is, oh, that's very similar, 0.7. We are told the probability of A given B is 0.5. And we're being asked in question 8 to get the probability of A and B. And then in question B, we're asked to find the probability of A or B. Right. You don't know if it's independent or not, but you can do a quick check. Are these two events A and B independent? I can tell just looking at these three values. Are A and B independent? Look at the value of A given B. Look at the value of A on its own. That's how you can tell. Are A and B independent?
No.
No. If these are equal, they are independent. If these are not equal, they are not independent, which means then I'm going to use the A and B formula. I'm going to find the probability of A given B and multiply it by the probability of B. And so it's going to be 0.5 times 0.7. And the answer then is 0.35. Are you comfortable about how we used the relevant formula and then just take the numbers and put them in? Let's do an A or B. If you look at an A or B, right, you're either this guy or this guy. So this one here works actually in all situations. So it's the probability of A plus the probability of B, take away the probability of A and B. Well, I know A is 0.4. I know B is 0.7. And I know this one because I found it out in question A. And if you put all this together, you get 0.75. So as long as you tell me the two individual probabilities and a conditional probability, can't I now find the ands and the ors? Right? So as long as you tell me these three guys, A, B, and the conditional probability A given B, I will be able to find A and B, and I will be able to find A or B. Okay, try that one again. Same question, different numbers. Probability of A, 0.1. Probability of B, 0.8. Probability of A given B, 0.2. And we're going to be asked to find the probability of A and B and the probability of A or B. Right, that's two guys. Are these two events independent? A and B, are they independent? 0.2 is not 0.1. So you want to get this fella. It's the probability of A given B multiplied by the probability of B. So it's going to be 0.2 times 0.8, which is 0.16. Are you comfortable about how we found that guy? Used this formula here to get it. Now, A or B, I guess I'll put it under here. Probability of A plus the probability of B, take away the probability of both of them happening, A and B. This guy is 0.1, this guy is 0.8, take away that guy. The answer is going to be 0.74. One lush version of this. Probability of A is 0.4. Probability of B, 0.6. Probability of A given B is 0.4. Are we good on that? Now, are A and B independent this time?
Yes.
Agreed? So, when you are going to find A and B, since they are independent, won't we use this formula, not that one? So it's just going to be the probability of A times the probability of B, which is 0.4 times 0.6, which is 0.24. Okay. Now, what about P, A or B? Well, that formula, the A or B one, doesn't really care, right? It works for all situations. So there's not like one version when it's independent and one when it's not. It doesn't matter. So we have the probability of A plus the probability of B, take away the probability that it's A and B. So it's 0.4 plus 0.6, take away 0.24, which is what, 1, take away that guy, so that's what, 0.76. So what I hope I'm getting across here is, if I tell you just those 3 probabilities, do you feel comfortable you can tell if they're independent or not? Do you feel comfortable you could find A and B probability and the A or B probability? So as long as I give you these 3 guys, you can tell me if they're independent and you can tell me what these would come to. Let's get by those. Oh, a new guy in town. This is called the complement of event A. And it'll be written as A with a little c above it. So the complement of an event are all the things that could happen that are not in event A. Which is just a long-winded way of saying, isn't the complement of A not A, right? Whatever's not A. So, for instance, if A was rolling a dice and getting an even number, won't the complement of A be getting an odd number? If A is it's going to rain tomorrow, won't the complement of A be that it's not going to rain? We'll call that dry. So the complement of A is the exact opposite of A, right? Now, if you take the probability of any event A and you add the probability of its complement, the answer is always 1. Because in the big scheme of things, it either happens or it doesn't happen, right? So together, isn't that everything that could happen? Right? It's either odd or it's even. It's either rains or it doesn't rain. But you can add them together, it's going to work. In fact, aren't A and its complement always mutually exclusive? Does that make sense? That any event and the exact opposite of that event, aren't they by their very nature going to be totally mutually exclusive, right? Nothing in common. Now you can actually rearrange this formula to find the complement. Can't you just take it away from 1, the probability of A, right? Mathematically, these are equivalent. Are we good? Complement of A just means things that are not A. The questions that they ask are maybe not what we're going to think they were. I'll get some in the chat. Will we see any operators? No, we don't use that notation. Oh, somebody thinks if I win the lottery, I should be able to make it rain with that kind of money. I could pay for it. I think that's what we're getting at. Right, let's make this a little bit bigger. I'm not sure what kind of screens you're using. Here we go. So consider these 2 events for a driver. A is the driver is under 25 years old, and B, the driver has received a speeding ticket, right? So he's had a speeding ticket, I guess, sometime in his career. Here is a probability in English, and one of these, oh, darn it, in space. I hate it when it does that. There, go away. I wanted that for earlier on, but I don't want it now. Go on. Yes, we are. Okay, so pretend you didn't see that answer. I actually probably jumbled it up anyway, the way Web assigned this. The probability that the driver has received a speeding ticket and is under 25. Now, the key word in this English sentence is and so that kind of matches with that one, would you agree? And A and B, yep, that would be the dot. Now, this one I don't think we saw. The probability that a driver who is under 25 years old has received a speeding ticket. Now, the English language don't always write things in the order that you want them to be written. So this bit here, haven't they told me that he's under 25 years old? That's a conditional probability then. And isn't that the B? No, the A, sorry. The driver is under 25. You are telling me he's under 25. And so it's a ticket, that's B, given it's an A. So that's this one here, right? The probability that I've received a ticket, B, given that I'm under 25, which I am. So this one is the probability that a driver who has received a speeding ticket, so it's a conditional probability. So it's either this one or this one, is over 25 years. Now, if A is under, isn't that the complement of A? Right? A is under 25, complement of A then is 25 years or older. So we are trying to find, oh, I've already picked it. So these are the kind of sentences turns into a probability. Here's a whole bunch more, same idea. And now we're moving on to less theory and more actual numbers, right? How these various rules can be used to calculate probabilities. And in a lot of ways, they are probably easier to do. So here is M&M candies. Did you know that they have, you know, when you get the mixed bag, that they're not evenly distributed? In other words, you don't get the same greens as you get orange as you get red, evidently. Did you know that, for instance, red and yellow are very popular colours and you don't get so much green or blue? Did anybody ever know that? Now you do. M&Ms, there are more of some colours than there are of others. Now, I don't know, maybe because people like red, they want more red M&Ms. Don't they actually taste exactly the same? It's just a food colouring on the outside. So psychologically, couldn't they make them all green and it wouldn't matter? Except psychologically, don't you like lots of different colours because you think you're getting something? So human mentality is weird. So what's the chances that you get a green or a blue? Well, I know that there's 7% green, and I know there's 7% blue, and you might think that the answer is 14%, which it is, but WebAssign wanted that number, not 14%. How do I know it wanted that number and not 14%? Point 0.14. Say again, Brandon?
Because it's out of 1. 0
well,
1,
that's true. They are out of 1, but it's a simpler clue than that. If they want percentages, don't they put a little percentage symbol outside the box? That's, yeah. My question wasn't much of a question now, but it just, you know, you'll do the right answer, right? You'll put in 14, which is right. It is 14%. And WebAssign's going to keep saying wrong, wrong. And what you tend to do there is, instead of going for the obvious, oh, they just wanted 0.14, aren't you going to start saying, oh, I'll look at one of those rules. Maybe it's the one where you take this away and add that or multiply this. You know, all sorts of weird rules that don't work because you thought you were wrong because you put 14 down. So always be on the lookout for that. Now, are these events mutually exclusive? Is getting a green candy mutually exclusive from getting a blue one? If you're a blue candy, can you be a green one? No, that makes you mutually exclusive then, doesn't it? Right, you can't be both at the same time. You're mutually exclusive. Right? That's a quick way of looking at it. Now, what's the chances you get a yellow or a red? There's yellow, there's red. I make that 40%. I'm going to put in 0.4. And are they mutually exclusive? And then the last one, find the probability that you're not purple. Now, if I wanted to know not purple, wouldn't I just add all these together? Would you agree? Not purple. I'd add up the yellow, the red, the orange, and so on. That's not purple. And I know that answer is 81%. But couldn't I do it this way? You are purple 19% of the time. Won't you be not purple the other 81% of the time? So I've actually used the complement idea just to make my calculations easier. So 0.81. Now, do you notice on this question, percentages on the outside? So this time you don't put in 0.14, don't you put in 14 if that happens to be the answer? Little things like that can bug you. Can you imagine you get really frustrated because you think you're right and it's saying you're wrong and all that kind of, that's all that would be. Now, if someone said to you, what is the probability that a toy is purchased for someone who's 6 years or older? In this table, 6 years or older happens to be all of those people, isn't it? All those kids, right? 6 or older. So that's going to be 20, 30, 40, 50, 58, 65, I believe. 65%. And I'll let you play with that one. And now I'm going to go back to notes. Oh, that would be a good idea. Someone's saying, you know, if you made them taste different, right? So a red M&M tasted like cherry and a green one tasted like pistachio or something, right? Wouldn't that make them more interesting? Yeah, you're right, it would. Right, now I must be hungry. That's making me think of food. Right, let's look at a new situation. This is repeated events. So this is where you do two things, right? So in the first story, there's going to be two dice. And one of them is going to be blue. And the other dice is going to be red. And we are going to throw two dice. In other words, we're going to repeat the event. If you think about it, one way of doing it is you roll the blue dice first, right? And you write down what happens, then you roll the red dice. So you're doing two events, right? Rolling one dice, then rolling the second. And we are going to be looking at probabilities of how that would work. Right, so.
Or is it just me?
Say again?
I can't really see your screen right now. I see you, but not.
Oh, I don't know what I'm doing. Let me go back in and out. Can you see the screen now, the red and blue? Does anybody see
It's
red
still
and blue?
loading for me.
Oh, so Mackenzie, you can see
break.
it. So it sounds like it might be on your side, unfortunately.
Yeah, you're good. I can see you just fine.
Okay, so let's look at how you calculate probabilities of repeated events. And when you do repeated events, you have two situations. And the ones that we're dealing with right now are independent events. Would you agree that if I roll the blue dice, it doesn't matter what number ends up being on the table? Would you agree when I then roll the red dice, it doesn't care what the blue dice is? Would you agree they're totally unconnected? That's the most common situation you're going to deal with. So we have repeated events. So the probability that, say, the blue dice is a 6, right? And so that's the math, and the red dice is a 2. We'll call that A and B. You simply just multiply them together. So the probability that you roll a blue dice and it's a 6, isn't that 186? And the probability that you roll a red dice and it's a 2 is also 186. So the answer is multiplication 1 out of 36. Does that seem reasonable, right? Two events, multiply them together. Now, let's make it a little bit messier. I'm just going to say blue is 6 rather than write the blue dice is 6, right? So the blue dice is a 6, right? And the red dice is a 2, or The blue dice is a 3 and the red dice is a 5. Now, this is a complicated probability because it's really made up of a number of things happening. This guy or this guy. So the first thing I'm going to look at is the or. Right? Now, what's the probability that you get 6 and then a 2? Well, that's going to be the probability that the blue one is a 6 times the probability that the red one is a 2. And that ends up being 1/6 times 1/6, which we know is 1/36. Now over here, the blue is a 3 and the red is a 6. Well, that's going to be probability that you get a blue one is a 3 times the probability that the red one is a 5. And that also ends up being 1/6 times 1/6, which is also 1/36. Now, what calculation do I do here? Do I add these two answers or do I multiply these two answers?
Add.
So you end up with 2 out of 36, which is 1 out of 18. That's very uncommon, but I put that one in because question 11D is like that. So if you repeat events and they are totally independent of each other, can't you just multiply 1 times multiply 1 times multiply 1? So let's put that into effect. Suppose I take a coin. Would you agree that it's either a tail or a head, right? And they're mutually exclusive, which is fine, but they're independent, which is more interesting. I would like to know what's the probability that I get 4 tails in a row, right? So I throw the coin, it's a tail, then again, and then darn it, the 4th time, still a tail, right? That would be quite hard, you would agree. But how hard, right? What's the probability of it? Well, since all of these are independent of each other, can't I just find the probability of each one and multiply them together? And the probability of a tail is a half. In fact, it's always a half because they're independent of each other, which means 1/16. And just because I want to, I'll turn that into a decimal, because maybe the next time they want a decimal, and I'll turn it into a percentage. Now, if they asked you that question in WebAssign and they say, as a fraction, it's pretty obvious they want that one. Agreed? As a proportion, or they might say to, 3 decimal places, they might phrase it like that. Don't they want that answer? And if they do a box with a percentage outside, they want that answer. And the reason I'm pushing this is I get lots of emails in the past from people saying, I got the answer 1/16, and this is me. I don't know what I've done wrong. It looks right, but WebAssign keeps telling me I'm wrong. Couldn't it simply be that you've written this and it wanted that? Or you've written that and it wanted this? Or who knows what it is? So fractions are fractions. Proportions, or to 2 decimal places, sometimes they phrase it decimal. If there's a box with a percentage outside, it's a percentage they're looking for. And that way, it's the same answer, right? It's the same thing written in 3 different forms. How are we doing so far? Right. Would you agree applying these rules is a little bit easier than the theory A given B and all that way numbers? It's a little bit easier when you can get your head around it. Let's do dice again. So what's the probability that you roll 2 dice and the total is 7? Now that's a real awkward one to calculate, because you could try and find out all the ways to do it, And we could do it in the form of some kind of multiplication, which I certainly could do that and find each one and then add them all up. We agree that would work, right? And I'm going to show you that and then show you why I'm not going to do that method again. Remember, your dice are two different colors. So I need to find all the different ways to get 7. And I'm even going to use color to emphasize. So the blue one, would you agree a 1 and a 6? A blue 1 and a red 6, doesn't that add up to 7? Right. Now, in our world, isn't that the probability of a 1 times the probability of a 6? And aren't both of those 1/6? So the answer to this is 1/36. Would you agree? 1/36. Right. Now, couldn't I end up with a 2 and a 5? Would you agree? Blue 2, red 5 adds up to 7 as well. Would you also agree that it's going to eventually be 1/36 when I've finished? What's the next one going to be? The next combination that adds up to 7?
3 and 4.
Yeah. Can you see this being quite laborious? Would you agree you eventually get 1/36 again? You with me so far? Right. Keep going. What's the next one?
4 and 3.
Yeah. And you might think, but we've already done a 4 and 3. Not really. Isn't a blue 3 and a red 4 different than a blue 4 and a red 3? Wouldn't they two different events? You imagine you saw them and I took a picture. Wouldn't they be different colored dice with different numbers on them? So those count as separate. You see that? Separate events. Does the color help you distinguish that 3 and 4 is not the same as 4 and 3? Right. A blue 3 and a red 4 is not the same as a blue 4 with a red 3. They both add up to 7, but so does that add up to 7, right? But they are different ways for it to happen. But it's also 1/36. The next one, I believe, is going to be a blue 5 and a red 2. And that's going to add up to 1/36. And the last one, if I get this right, is a blue 6 and a red 1. And that also adds up to 1/36. So the probability that 2 dice give you a total of 7, isn't it made up of each one of these events added together? And there's 1, 2, 3, 4, 5, 6 of them. So 6 out of 36. And after all that hard work, do you know if you roll 2 dice, the chances you get a 7, as you're told, is going to happen 1 out of 6 times? Would you agree that's a lot of work? Especially if you have to do adds up to 11. Can you imagine how many of them there are? Adds up to 6, adds up to 2, adds up to 4. So I'm going to show you 2 ways to do that same question. Here's the second method. What's the probability of getting 2 dice and the total is 7? Put 36 on the bottom. Now you might say, why 36? If you think about it, isn't there 6 times 6? That's 36 things it could happen, right? If we went through every single combination, right? Blue 1, blue 2, blue 3, red 1, red 2, red 3, all the way. There's 6 rows and 6, 36. And then you just go through it and you say, how many ways can I get a 7? So you go 1 and 6, gotcha. 2 and 5, 3 and 4, 4 and 3, 5 and 2, and then the other one. So on the top, you just count all the ways. to get total of 7. Right, let's try this method. What's the probability that you throw 2 dice and the total is 11? Now, the bottom is always going to be 36. How many different ways can you get 11 with 2 dice? 2 ways. Agree, Brandon. 5 and a 6, and then a 6 and a 5. Agreed? 5 and 6. So 2 out of 36, 1/18. Bit harder. What's the probability that you roll 2 dice and the total is less than 4? Now, you might want to do a bit of scratch paper with this. Less than 4 means the total was a 3. It also means, doesn't it, that the total could be a 2. Why doesn't it include the total could be a 1? Why is that silly?
Because you have 2 dice.
Yeah, you're never going to get a total of 1, agreed? Now, how many ways can you get a total of 2? Can't you just get it with a 1 and a 1? Oops, sorry. Sorry about that. We've got something being delivered and I had to, for some reason, I thought it was going to get delivered today. So, only one way of getting a total of 2. How many ways to get a total of 3? Would you agree a 1 and a 2 and then a 2 and a 1? Do you know you reverse the choices? So altogether, isn't there 3 ways? 1/12. Compared to writing them all down and adding them all up, which is my first method, do you like this one a little bit more? Is this one less work? Does it still make sense to you how you would do it? Now, I promised you a third way, and I will. It's a pain in the butt, but the third way is sometimes the only way to go when the probabilities they ask you about the dice get kind of messy. So what you have to do, and you only should do this once and keep the piece of paper. So I'm going to have the red dice here. So the red dice is 1, 2, 3, 4, 5, 6. And now I'm going to do the blue dice choices here. That's going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. If you look in here, do you see there's 6 and there's 6 rows? Do you see the 36 things that can happen? So what you do is you write this table down. Now, once you've done it once, can't you just count the things and use it over and over again for different totals, for example? So I'm not going to color scheme them, that would just take too long. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. And I'm making red the first dice, so that's why it starts with 1s. And now it gets kind of monotonous. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Then you go 3, 1, 3, 2, 3, 3. Yeah, I'm going to be here forever, aren't I? But I kind of need to keep going till I'm finished. Well, I'm halfway through. 4, 1, and then 2, and then 3, 4, 4, 4, 5, and 4, 6. Almost done. All the 5s. And then lastly, all the 6s. That's a pain in the butt, but if you keep that piece of paper, it's done, right? You only need to do it once and you can use it for lots of questions. So suppose I went and said to you, what's the probability that the total was 8? Now, I know there's 36 things here, so 36 goes in the bottom. I just need to find out where 8s live. Now, here goes. Would you agree that adds up to 8, that adds up to 8, 4 and 4, 3 and 5, 2 and 6. There were 5 of them, and there's my answer. Now, I can even do, what's the probability that the total was more than 9? So a total more than 9 would be what? A total of 10, a total of 11, a total of 12. Agreed? Now, if you look at when a total of 10 happens, I don't want to draw on this thing because I spent so much time doing it. Do you see that diagonal of 3 numbers, 3 pairs? Have you noticed that diagonals add up to the same amount? 10, 10, 10, so 3 of them. 1 and 2, 4, 5, that one's 6. Do you see the answer is 6? But you can use this for questions none of the other methods worked for. So what's the probability, right, that the first one was even, so that would be the red one is even, and that the blue one, that's the second one, was also even. So I'm basically saying, what's the chances that you roll 2 dice and both numbers are even, right? That would be an easier way to say it, right? Both of them are even. So when you just hunt through these and find only the things that are even, great. So would you agree that's both of them even? So that's 1, 2, 3. Nobody there counts because one of them's odd, right? So I've only got 3, 4, 5, 6. None of these count. 7, 8, 9. And so I get 9 out of 36, which is quarter. Are we okay with the 2 dice thing? You may have to use this table for some of the more complicated ones. Certainly, I don't think I'd want to do that question here, both even, without having this in front of me. Once this is in front of me, isn't it pretty easy to count them? If you were trying to write down all the different ways in which both are even, could you miss one if you were doing it by just counting? Just method 2. Any questions? A lot happening today, agreed? A lot to take in. So let's